Uh, okay, so let's start. Okay. So hopefully my screen is visible. Okay. So um, yeah, my screen is visible, right? Uh, okay. Okay. So uh, okay. So we will just start from the factorial. Obviously, most of I mean everyone already knows what the factorial is, but for the sake of completeness, I will just review it, which is the number of number of ways uh, an object can be arranged in a line. So uh, this is the number of ways an object can be arranged in a line. Like you obviously all know that this is this is uh, basically you have n ways to choose where the first person goes, and then n minus one ways to choose where the second person goes, and so on. Like basically it's just that. Okay, so now you can from this you can derive what NCR is, which is basically the number of ways to choose our objects out of n, and you can like basically uh, if you think about it, like if I want to choose our object out of n, and uh, okay, okay, okay. Uh, so right. So this is the number of ways to choose our objects out of n, and you can basically derive a reference for it by observing the fact that Okay, so basically, uh, you can derive a recurrence for NCR by thinking about what if you have to choose R objects out of n, but you have one special object, like you have to choose one special object out of those R objects. So basically, you can write this in two ways, which is R times NCR, because you can first choose the R objects and then choose that special object, or either you can choose the special object initially and then just n minus 1 C R minus 1. So uh, basically, this gives you a recurrence where NCR by equals n by r times n minus 1 CR minus 1, and then you can apply this recurrence again to get n by r times n minus 1 by r minus 1 times n minus 2 CR minus 2, and so on. And at some point you will reach r equals 0, and the number of ways to choose 0 objects out of anything is 1, because it's just choosing nothing. Like choosing nothing is also choosing something. Like you can think about that. So this is going to be at, until that point. So basically n times n minus 1 and so on until n minus r plus 1, because when the lower term becomes 0, this will be n minus r. So you will have an n minus r plus 1 before that. So n to n minus r plus 1, the product of consecutive numbers, and divide that by r factorial. And you can also write this in a slightly more convenient form, which is n factorial by r factorial times n minus r factorial, because you basically skipped everything from 1 to n minus r in the numerator when you got till 0, and in the denominator you already have an r factorial, so you can write it like this. And like basically there are a lot of proofs for this. There are two or three more proofs for this. You can like look for them online or something, but now we can move on. So basically in a competitive programming context, since these numbers get very large very quickly, you are usually asked to find them modulo some large prime numbers. So in order to find those modulo some large prime number, what we need is some modular arithmetic. So basically, uh, modular prime number always, like I will not be proving this, but you can prove this, and it's not that hard to prove. So for any uh, a like 0 less than or equal to 1 less than or equal to less a less than p, you define the inverse as the unique number, and this is going to be unique because if there were two b's, say b1 and b2, you could equate them and get a contradiction. So one we define this as its inverse, like basically 1 by a as the unique number b such that ab is congruent to 1 mod p, and you can show that this always exists. Or okay, let's just do it. Basically, from 0 to p minus 1, the elements like you choose b equal to 0 to p minus 1, the value can never repeat, because if a b1 is congruent to a b2 modulo p, then since A is not congruent to 0 modulo P, you have that B1 is congruent to B2 modulo P, which is a contradiction because we assume that the two B's were different. So basically, the B's are all, for different b's you get different values of ab. So since there are p different b's and p different values, each value must have been achieved exactly once, and 1 is also one of those values, so 1 also must have been achieved exactly once. So there exists some b's such that ab is congruent to 1 mod p, and what we call this b is the inverse of a. And basically what this tells is that division is defined modulo under modulo p. Uh, so basically, what you can do is stuff like uh, basically uh, a to the p minus 1 is congruent to 1 mod p. What you can do is stuff like say like a to the p minus 1 is 1 mod p, and like this is Fermat's this is Fermat's theorem. And you can what you can do is, since we know now that division is defined modulo p, we can say that a to the p minus 2 is congruent to 1 by a mod p. And so basically 1 by a mod p, instead of evaluating 1 by a mod p, you can just evaluate e to the p minus 2 mod p. And usually that turns out to be quite a bit easier than evaluating 1 by a mod p, because we have something called binary exponentiation, where uh, basically let's say you want to calculate e to the b mod m, where b is say like 1 to 10 to the 18. So obviously normal multiplication is out of the question. So what you can do is that you can calculate a to the 1, a to the 2, a to the 4, and you can calculate this easily because each term is the square of the last term, so you can just use the information from the previous terms, and you can do this till a to the 2 to the 60. And now you can take the binary representation of b and take every a to the 2 to the k that appears in it and multiply all those a to the 2 to the k, because you already know all of those. And you can, so you did this in O of log b time. So uh, this is really fast for most competitive programming contexts, where p is usually 10 to the 9 plus 7 or 998244353. So basically, a to the p minus 2 you can evaluate. So basically, this was how to divide by a prime number. This was how to divide by something modulo prime number in a competitive programming context. So now you uh, now you can say that the binomial coefficient is this, NCR is this. So now you can think about like recalculating the factorials. Like usually in competitive programming context, n is 10 to the 5 or 10 to the 6 at the most. So basically, and r is obviously less than or equal to n, because the number of ways of choosing, like you can't choose more than n objects from out of n objects basically. So r is less than or equal to n. So r is also fairly reasonable. So basically, you can pre-calculate all your factorials, and the way you do that is very similar to how you do prefix sums, where factorial of I is I times factorial of I minus 1, and then you run that for I equal to 1 to 1 10 to the 6, and 1 to 10 to the 6. So basically, if you can calculate factorial of n modulo that prime, uh, uh, yeah, and this is modulo p by the way. So basically factorial of n, and we already know how to divide by something modulo p. So uh, this is just this, and since we already learned how to divide by something modulo p very fast, so basically NCR can be calculated really fast in like O of log p time. So this was how to calculate NCR in your competitive programming context. So, do you have any questions till now?
Can you please tell the problem once?
No, we were not doing a problem. We were just like uh, reviewing some stuff. Like basically, probably you all know this, but I was just doing it for the sake of completeness. Where so first n factorial is the number of ways n objects can be arranged, and NCR is the number of and then the inverse, the existence of inverse is modulo p, and then how do you calculate an inverse modulo p in a competitive programming context or in any general context, because binary exponentiation is useful. Even manually you can calculate stuff like 2 to the 10 to the 9 modulo whatever, and then we learned how to do NCR mod p using the above stuff. So you can basically, yeah, this was not uh, a problem. It was just some like theory. Okay, so if nobody has any questions, I will just move on. So the next thing is binomial theorem. So let's say you want to expand a plus b to the n. Now this has n brackets, a plus b times a plus b and a plus b. So basically, obviously all the terms are going to be of the form e to the r, b to the n minus r, because like from each bracket you are going to choose either a or b. So basically, you don't have a third variable. So a to the r times b to the n minus r. All the terms are going to be of that form, and obviously some coefficient, let's say c. So basically, this corresponds to choosing a from r brackets, and once you choose a from r brackets, you are basically bound to choose b from the other n minus r brackets. So basically, c is going to be NCR, because once you choose A from R brackets out of these n, you need to choose B from the other n minus R bracket. So basically, once you choose the A's, the B's are fixed, and the number of ways to choose A is the number of ways to choose R objects out of n, which is just NCR. So basically, what you can say is that this is I equals 0 to n NCI times e to the I times b to the n minus I. So that is binomial theorem, and what you can do is that you can like generalize this. For example, if you have a plus b plus c to the n, then you can kind of think about like uh, basically this is just there is uh, this is the multinomial theorem, where basically you just generalize what you did in the binomial theorem, where if here the coefficient will be of the form a to the I, b to the j, c to the k, where I plus j plus k is n, and the number of ways to do that is first you choose n c like I out of the n to be a's, and then you choose j out of the remaining n minus I to be these, like basically you choose j brackets out of the remaining I, and from them you choose b, and then you choose, like basically there is nothing left to choose. Obviously the other stuff is just one, so that is times n minus I minus j choose k, and this is n factorial by n minus I factorial, uh, I factorial, and this is n minus I factorial by j factorial n minus I minus j factorial and n minus I minus j factorial. Basically, you don't even need to expand the last term because you know that it is going to be 1 because n minus I minus j is equal to k. From here, you get that this is just 1, but I am just expanding it because. Uh, so basically, this is just going to be 1, and these two are also going to cancel. So basically, this is n factorial by I factorial j factorial n minus I minus j factorial where and n minus I minus j is just k. So n factorial by I factorial j factorial k factorial. So basically, and we have also have a convenient way to write this, which is n c I comma j comma k. Uh, Basically, this represents n factorial by I factorial, j factorial, k factorial. And of course, you can generalize this to any number of variables. And I think it is fairly clear from the three variable case how to generalize it for n variables. So, uh, like basically, binomial, the use of binomial theorem is that you can evaluate stuff such as this. Okay. So like basically the usage of binomial theorem is that you can evaluate stuff uh, like this. Uh, okay, let's say uh, equal 0 to basically what you do to evaluate stuff like this is that you just use roots of unit like basically okay I don't say I think should not go into that. So, okay, so basically the use of binomial theorem is that like in that you can also evaluate stuff like this where like it's like nc0 plus nc3 plus nc6 and so on. So you can also evaluate stuff like this, but I like I don't think I have seen that uh, it's it is a little advanced use of binomial theorem, but I have never seen it used in a competitive programming context. So we will not do that. Like stuff like let's say NCI times 2 to the I. So basically you can that's just 3 to the n because you can treat this as NCI times 2 to the I times 1 to the n minus I, and you can write that as 2 plus 1 to the n, which is yeah. So basically, uh, in a competitive programming context, binomial theorem does come up very rarely, but uh, I like it is slightly useful sometimes. So we did that, and now uh, we can. The next topic is the principle of inclusion and exclusion. Uh, so basically, probably everyone knows the two-set version where you have this where A union B denotes the union of the set and A intersection B denotes the intersection of the set. And now, basically, for this, the intuition for this comes from Venn diagrams where this is A intersection B, this is like this entire thing is A and this entire thing is B. Like basically you are double counting but then you are fixing it. So that that is the two variable form, and also the three variable form is also not that hard to get from the Venn diagram where this is basically you count the inner region thrice when it should only be counted once. So you subtracted this B intersection C, C intersection A. But now this But now the problem is that you subtracted this small region, like basically you added it three times in A plus B plus C, but you also subtracted it three times when it should actually be there exactly once. So you also need to add it back in. So A intersection B intersection C, you add the small region back in. And the general principle of inclusion, I think, is fairly clear from here, where you have alternating pluses and minuses depending on the cardinality of the intersection you are taking. For example, the four variable version is something like this. Basically, in the case of even cardinalities, you will subtract, and in the case of odd cardinalities, you will add. So it is like this. Uh, uh, Basically, this is not that easy to see using Venn diagrams, so uh, we will try to prove it generally for n sets using binomial theorem. So uh, let us consider an element x which appears in at least one of this, like let's say our sets are a1, a2, and an. And let's say there is an element x which appears in the set ai1, ai2, so on until aik, where k is greater than or equal to 1. Otherwise, for k equal to 0, it will be counted exactly 0 times. Uh, and for k, we will show that for k greater than or equal to 1, in this summation where you, for odd cardinalities you add and for even cardinalities you subtract, we will show that x is counted exactly once in this sequence of additions and subtractions. So basically, what you do is that let's say that we selected an odd number of subsets basically. Okay, so let's suppose we selected the null set out of these. So obviously the null set will not be counted because uh, x does not even appear in the intersection of those. But uh, let's say we pick some non-null set out of these. So let's say AJ1, AJ2, on until AJL, where all of the J's, like for example, okay, I'll take some example where let's say we have the 5 element version. So this is let's say 2, 4. This is let's say 1, 3. This is let's say 1, 4, 2, 5. Let's say 4. Let's say this is 3, 4. Okay, so basically all of these are two element sets, and let's consider x equals 3. So it appears in A2 and A5. And notice that here we are always considering intersections. So x will only appear in an intersection when it appears in all the sets that we are taking the intersection of. So for example, if we take the intersection of A2 and A3, x will not appear in that. So uh, when we take, and even when we take the null set, x will not appear in that. So we basically need to show that except the null set, basically the even times when, as you can observe above from the n equals 4 case, whenever a subset has even cardinality, it gets subtracted, and whenever a subset has odd cardinality, it gets added. So basically, everything I'm not n. Let's say, what did I say? Oh yeah, k. Okay, so kc2 plus kc4 plus, uh, like basically the odd terms are going, sorry, the even terms are going to get subtracted, and the odd terms are going to get added. So, and we need to show that this counts x exactly once, because uh, that's what we want, right? It should appear in the union exactly once, because a set cannot contain an element two times. So basically, let's assume that we added kc0 as well, and kc0 by definition we saw above that is always 1. So basically, we now need to show that uh, kc1 plus kc3 plus equals, uh, and now since we added kc0 as well, you can think about this one as kc0. Okay, so kc0 plus kc2 and so on. So basically, this what this is trying to say is that the number of ways to choose an even size subset of k from a set of k elements is equal to the number of ways to choose an odd size subset from a subset from a set of k elements. So there are a couple of ways to prove this. We will see two here. One of those ways is that you can consider some special element. Let's say x, not x. Let's say we consider that element e. You can consider some special element e where uh, e should, uh, where, and whenever we consider, let's say we consider the set of subsets of the, that set with even elements, like for example, if we have the set 1 2 3 4, then this would contain the set itself, because that has an even cardinality, and 1 2 and 1 3 and so on, like basically everything with a cardinality of 2. Now let's say we consider the element 4, and for 4 what we will do is that whenever we will see that 4 is present, like let's consider a subset with even cardinality. So whenever we see that element, see that that element is present in our set, we will remove it, and if we see that that element is not present in our set, we will insert it into the set. So for example, for if we had 1 2 initially, then after we are done with it, it would become 1 2 4. And if we had 4 1 2 3 4 initially, then after we are done with it, it would become 1 2 3. So 1 2 3, and basically you can show that this process always produces a unique subset, and the key part of this process is that it always produces a subset of odd cardinality, because once you are either adding an element or you are removing an element from a subset of even cardinality, and that will change its parity no matter what. So it becomes a subset of odd cardinality after that, and it still remains a subset, because obviously when you remove, there is, it obviously is going to remain a subset, because it was a subset before and now you are removing something from it, so it will remain a subset. But if it is, uh, uh, if it did not contain that element before, even after inserting that element, because that element is itself, like basically that element is itself belonging to our set. For example, like after we are done with that, it would become 1 to 4. So 1 to 4, like 4 itself belongs to S. So even after adding it, it doesn't change the fact that a subset belongs to S. So basically, they are unique subsets, they are of odd cardinality, and they all belong to S. So basically, we have showed that there exists a mapping where every element in the set of subsets with even element maps to a set in the maps to a set with odd cardinality. Basically, every subset with even cardinality is mapped to a subset with odd cardinality, and all such subsets are unique. And similarly, and you can note that anything we used here did not use the fact that the subset size was even. So the same argument can also be used for the odd size subset, where uh, there exists a mapping from the odd size subsets to the even size subsets as well. So basically, there exists a bijection between them. So the cardinalities of the two must be equal. So that's the first proof, which is a combinatorial proof, and the second proof, which is slightly easier, like you don't need to think as much about it, is that you can consider the expansion of 1 plus minus 1 to the k, which is kc0 plus minus 1 to the 1 times kc1 times 1 to the k minus 1, but that does not change anything, so I am not writing it. Plus minus 1 to the 2 of times kc2 and so on. And expanded this using binomial, and this means that 0 is equals to 0 is equals to kc0 minus kc1 plus kc2 and so on, which is basically what we wanted. So it is slightly more straightforward than the previous proof, but it does not give you as much insight as the previous one. So combinatorial proof usually tend to give you more insight into the particular thing that you are doing. And now let's see some combinatorial identities which can usually be proved algebraically as well, but uh, they are sometimes easier to prove using combinatorics. So this is combinatorial identity. So basically our first identity is that NCR plus N plus 1 CR is equal to N plus 1 CR plus 1. So let's think about, like, out of a set of N plus 1 objects, you are trying to choose R plus 1 object. So either you can choose the last object or you won't choose the last object. If you do choose the last object, uh, then basically you take NCR with, because now there are n objects remaining to choose. Oh wait, I think I wrote something wrong here. Wait a second. So yeah, okay. Sorry, I wrote something wrong here. NCR plus NCR plus 1 is equal to N plus 1 CR plus 1. So basically, either you can choose the last object or you will not choose the last object. If you do choose the last object, then there are NCR ways to choose the remaining objects, because you have n remaining objects and you already chose one out of the R plus 1 that you needed to choose, so that's NCR. And either you will not choose the last object, in which case you have a quota of R plus 1 left to choose, and you also have n elements in this case because you have decided not to choose that element. So you only have n elements for which you have a choice. So NCR plus NCR plus 1 is equal to n plus 1 CR plus 1. And of course, this can be proved algebraically as well. And that just follows from the definition, which is not too hard. So uh, you can do it yourself. And the next identity is the famous uh, hockey stick identity. Hopefully, I write this one Okay, so basically, uh, what you can do is that you can think about like extending this idea. So basically, is on the right hand side you get n plus 1 cr plus 1. Okay, on the right hand side you get n plus 1 cr plus 1. Okay, so on the right hand side you get n plus 1 cr plus 1, and now you take cases. Here you took only cases on whether it was the last element or not, but you can think about somehow choosing some more cases. Like for example, you can think about like uh, choosing the minimum element. Basically, uh, you can so let's draw the n plus one objects in a line. So basically, they are represented by dots. So these are n plus 1 objects, and out of them you have to choose r plus 1. So either the like let's number them from 1 to n plus 1, and basically uh, you can take cases on what your minimum element is going to be. Like the object with the minimum index that you choose, what is it going to be? So basically, the first uh, element, like the first object is uh, like the first. If you choose the first object, then you are going to have like if you choose the first object as your minimum object, then you have ncr ways to choose the other r objects because you already chose the state of the first object, and you have like basically the same logic as the above. And now let's say you choose the second one as your minimum object. Now you can't choose the first one because that would contradict the fact that the second one is your object with minimum index. So this will have n minus 1 cr ways and so on. You can only go up to a certain point, which is RCR, because R minus 1 CR is once again, after that point, you are going to be 0. So this identity is sometimes called the hockey stick identity uh, because of the fact that when you like, okay, wait, I think this section ended. Uh, so, okay. So basically, when you draw the Pascal's triangle, uh, it sort of looks like this, which is like, uh, okay, this is 0 C 0, and this is 1 C, like this is 0 C 0, this is 1 C 0, 1 C 1, 2 C 0, 2 C 1, 2 C 2, and this is 1 3 3 1, and this is 1 4 6 4 1, and this is 1 5 10 10 5 1. Okay, so this is enough, I guess. Uh, so basically, if you take the stuff corresponding to this identity, uh, basically this is 2C1, like from here you took 2C1, from here you took 3C1, from here you took 4C1, and from here you took 5C2. So basically, what our identity says that 2C1 plus 3C1 plus 4C1. Okay, wait a second. Wait a second. Yeah. Okay, sorry. Okay, this entire thing. So basically, what our identity says is that 1C1 plus 2C1 plus 3C1 plus 4C1 is 5C2, which is true because 1 plus 2 plus 3 plus 4 equals 10. And you can also see that here or here. And the thing is, when you draw it out on the Pascal's triangle, it kind of looks like a hockey stick. So That's why it's called the hockey stick identity. And the next series is called the hockey stick identity. And next identity is called the Vandermonde identity, where uh, summation from which okay. So the next identity is the Vandermonde identity, where MCR times NCK minus R is equals to M plus NCK, and this is also very easy to prove combinatorially, and also not like, and it's also very easy to prove algebraically. You can just use the binomial theorem again. So basically, what you can do here is that you have two sets A and B. Uh, let's say this is m elements and this is n elements, and you need to collectively choose k elements from A and B combined. So basically, you can either like you can fix the number of elements R you choose from A. So we'll choose K minus R from N. So basically, MCR times NCK minus R. Uh, that will be the number of ways in that case, and you take the summation over R from 0 to K, and in that case, and in the, or you could just count it directly where you have m plus n elements and you need to choose k out of them, and yeah, so basically you can either from r and r is from 0 to k, and also you don't need to worry about like what if k minus r becomes greater than n or something, because that won't contribute to uh, the summation anyway, because it's just going to be 0. So yeah, this is Vandermonde's identity, and the okay. So now the next thing we'll do is some applications of PIE. So uh, PIE you can use to calculate. Let's say, so there is something called derangements of a permutation. Like basically, uh, if you have 1, 2, and so on length, and like you have these places, and you need to put like you need to count the number of permutations such that no element is at its right place. Like basically, you have p like if you do not have pi equal to I for any I from 1, 2, and so on till n. So that is a derangement, and in order to count them, you can use pi. So what you can do is that basically you can uh, like fix the set of elements that are sure to be fixed points. So basically what we'll try to do is complementary counting. So complementary counting is where you have like basically n factorial minus number of permutations, because n factorial is the total number of permutations, and minus the number of permutations with at least one fixed point. Okay, so basically, n factorial minus number of permutations with at least one fixed point, and let's fix the fixed points. So basically, let's say P1, P, okay, not P1, okay. Let's say F1, F2, so on until Fk are the indices that are surely going to be fixed points. Like, we don't know about all the others, they could be fixed points or they could not be fixed points, but we know for sure that Pfi is Fi, like that is, those are fixed points. So basically, uh, we can like NCK because because like if you think about it, any set of k indices is indistinguishable for you because NCK, because like basically it doesn't matter what set you choose to be the fixed point, it doesn't uh, matter. Like basically everything is going to be the same for every set of k indices and times n minus k factorial, because you do not have the freedom to move these k indices, but you do have the freedom to move the other n minus k indices. And yeah, that's it. So basically we just take the sum from k equals 0 to n of this. No, obviously we don't do that because of the fact that when we only said that these are fixed points. We did not say anything about the rest of the points. Like as I said, they could be fixed points or they could not be fixed points. So basically, one permutation could be counted like 2 to the number of fixed points times, because for any subset of the fixed points that you pick, there will be okay from k equals 1, but obviously it's still going to be wrong. So any subset of the k indices that you will pick, uh, uh, like the k fixed points you will pick, there that permutation will be counted in that subset. So basically, what do we do in order to fix this? We just use PIE, and yeah, that's like basically minus 1 to the k plus 1, because initially you add the permutations with one fixed point, like you fix the fixed points and then you subtract the permutations with two fixed points and so on. So basically that, and this is obviously not your answer yet because of the fact that you need to subtract this from n factorial, and uh, subtracting this from n factorial gives you a slightly better form for this. So basically what you can notice is that my this subtraction sign will flip the sign of all the terms to the right of it, so it just becomes minus 1 to the k, and also the first term is happens to be exactly n factorial, and c1 times n factorial times minus 1 to the 2, where this is n factorial. So basically this happens to be exactly n factorial, so it will just cancel out and everything else will just stay as it is, and as it not actually as it is, because you will not get negated, so instead of k plus 1 I can just write k. So this is your final answer, and let's just check that I didn't do anything weird. So basically let's say for an equal to 2 we want to check. So that is 1 2, and there is exactly one derangement because you can't, like there are only two permutations and only one of them is the derangement, and it seems correct for n equals 2, and for n equals 3 let's see that for n equals 3 there are going to be 2 3 1 2 1 3. Okay, okay, there will only be two derangements in this case as well, because yeah, and let's just check what we get from the formula. C1 times 1 factorial times CC2 times 1 factorial times minus 1 to the 2 minus 3 to 3 times 0 factorial, and uh, yeah, 3 to 3 times 0 factorial, which is just 2. So basically, this gives correct answers for n equals 2 and 3, so it is from correct place. I thought I was scared that I did some mistake in this, but okay. So basically, this is the formula for the number of derangements. And another thing that you can use PIE for is, let's say you have some range L to R and you have some number n, and you want to count the number of numbers that are co-prime to n in this particular range. So you can just take all the prime numbers dividing n. They are all distinct obviously, and P1, P2, so on till Pk, and you basically want the number of numbers in the range L to R which are divisible by none of the primes, and obviously principle of inclusion and exclusion can do that very easily. So basically we can just solve for 1 to R and 1 to L minus 1 and then subtract the two counts from each other. So basically floor of R by P1 plus floor of R by P2 and so on until floor of R by Pk, and then minus floor of R by P1 P2 because we counted that twice and so on. Like basically you get it right. It's just like normally how you write principle of inclusion and exclusion. We write this as well. Okay, so now uh, let's cover a bit about how would you write this in code. So in code, in code you would be like basically, let's say you have these k primes and you would represent which prime you are taking in your subset as a bit mark. For example, you have P1, P2, and P3, and you want to say okay, like I'll take this and this, so 101, and you will check whether to add or subtract that subset by checking the pop count of the mask that the bit mask that you use. So basically if the pop count is even, then subtract that, like take the product of all the elements in that subset and then subtract r by that, and if the number of elements in that subset is odd, then add the floor of R by the product of elements in that subset. So basically in code you can just do like represent subsets by bit marks. Basically that is the key point here. So the next uh, okay, so next we will do, hopefully you all know about recursion, where like this something is expressed in terms of its past terms. So basically, uh, for stuff like Jedi or something, you might need to like solve some characteristic equation or something. So basically, I'll quickly cover how to do that here. So let's say you have something like a bit nicer. Let's say like this. So basically, you consider the characteristic equation. This is actually uh, a bit hard to show how it works, but basically it does work. So basically you can consider this equation because, uh, for example, if it would be something like this, if it was something like this, then you would consider this equation because, like basically the idea behind this method is that uh, you assume P n equals C times alpha to the n plus uh, plus d times beta to the n uh, uh, where in the bottom equation, in this equation, like basically we didn't take square because the key idea is that you assume that this is alpha to the n plus beta to the n, and when you divide by alpha to the n minus 3, you basically, like, you are trying to solve this separately for alpha to the n and beta to the n. So basically, when you divide by alpha to the n minus 3, you get the cube here. So basically, what I wanted to illustrate is the fact that you basically need to write it as the sum of all its predecessors, like this, like 0 pn minus 1 plus 3 pn minus 2 plus minus 2 pn minus 3, like this. So, like, instead of here also it being x square minus 3x plus 2 equal to 0, here it will be x cube minus 3x plus 2 equal to 0, uh, because here you have a 0, like basically it goes, you need to divide by n minus 3 instead of n minus 2. So hopefully, so basically now if you are given some initial conditions such as p1 equals to 1 and p2 equals 2 or something, uh, so this gives you x equals 1 and x equals 2, and now you can just uh, solve for C and D, where this gives you C plus, it is C, yes, yeah, it is C. C plus 2D equals 1, and this gives you C plus 4D equals 2, and this gives you D equals 1 by 2. Wait a second, did I put something wrong? No, it's correct. Okay. D equals 1 by 2 and C equals 0. So I just picked this random example, which ended up giving us Pn equals 2 to the n minus 1. Like, this was easy to find by hand, but let's say I change this to a 3. In that case, you would get D equals 1 and C equals minus 1. So this would become Pn equals d times to beta to the n. What is beta? Okay, so 1 times 2 to the n plus minus 1, minus 1 times 1 to the n. So basically this is minus 1. So 2 to the n minus 1. So basically this was also a bit easy to guess, but basically, let's say I use something like x square minus 5x plus 6 equals 0. So x minus 2 times x minus 3 equals 0. So in that case, we'll have some linear combination of 2 to the n and 3 to the n, which is kind of uh, hard to solve if you don't know this characteristic equation thing. So basically, this is not that useful, but basically, if you don't want to use matrix exponentiation for recurrence relations or something, then this is a good option. Like, uh, you can usually get by for most recurrence relations without matrix exponentiation if you know this technique. But obviously, in some cases where it's something like your Pn equals, let's say, Pn minus a plus Pn minus b. In that case, it will be really hard using this method because the roots will be complex and it will be hard to solve for what are C and D in this case. And basically, you will have n roots. You are going to have max of a comma b roots as well. So even that is a problem. So, but basically, whenever you have like a term depends on previous two or previous three terms, you can usually get by with this method. So basically, this was how to solve uh, recurrence relation. Okay, so the next thing is that we doing some problems. Uh, so basically, this is you guys can like fix the problem. Uh, so basically, I'll just summarize this problem. Basically, you have even gold coins and even silver coins. Okay, it was exactly like this, right? Yeah, AI gold coins and BI silver coins, and for a gold coin, the value is determined, but for a silver coin, it is not determined, and for each silver coin, you have a probability where it will be 0 with probability half or 1 with probability half, and you have to answer few queries where in the ith query you need to calculate the probability that the total value of points in bags from L to R is strictly greater than the total value in all other bags. So basically, what really matters here is not the actual number of gold and silver coins in each bag. In fact, you can basically just assume them to be two large bags. Basically, only the fact that uh, it is outside or inside the range that we are concerned with matters. Basically, A1, A2, so on until AL minus 1, AR. Wait, okay. Recording is still happening, right? Yeah, it is. So, uh, okay. And AR plus 1, AR plus 2, so on until AN. Basically, this is the total value of the gold coins outside of N. This is determined already, right? This does not have any randomness to it. This is just done when, like, when you, uh, like, this is basically this. Everything here is determined already. Like, you can't change that. But what you can change is that BL plus BL plus 1 and so on until BR and B1 plus BL minus 1 plus BR plus 1 plus BR plus 2 BN. So basically, this is the total silver coin size. In fact, even the fact that this belongs to the L bag or the L plus 1's bag, that does not matter. Basically, you can just, all you care about are these four numbers. Like, everything else does not matter. So basically, what you can think about is that 0 with probability half and 1 with probability half is slightly hard to handle. So what you can do is that you can, like, have it 0 already, but it becomes 1 with probability half. So basically, all you can assume that every coin is already a 0, but it can become a 1 with probability half. Like, this is, it's easy to see that why this is an equivalent way of looking at the problem. But even this way, even just changing this way of looking at the problem will be really enlightening. So basically, now, uh, and you don't even care about this, you only care about the difference of the two values. So basically, if A1, A2, let's call this G0 for G outside, let's call this GI for G inside. So basically, uh, the only thing is that G outside plus silver outside should be less than gold inside plus silver inside. uh, right? So basically that's the only thing you care about. And for basically for the outside coins, what you can think about, so basically for the inside coins, you think about this, that they are already zero and they will turn to one with probability half. And for the outside coins, you think about the opposite thing, where they are initially one, but they will turn to zero with probability half. And the thing is, this probability half event can, it will only increase. Basically, what you care about is the difference Si. Yeah. What you care about is the difference Si minus So, and that should be greater than Go minus Gi. And don't worry too much about calculating these values, because that can be done easily using prefix sums, as you know. So we don't really need to worry too much about this. We can just assume that they are already given to us. So we know that Go minus Gi is the constant, and we also know that initially, if you consider like this is the main value that we are concerned with, so let's name this D. So it's easy to see that one coin inside the range, one silver coin inside the range, turning to value one, like one silver coin inside the range which initially has value 0, turning to value 1 will only will increase d by 1. And also one silver coin outside the range which initially has value 0, which initially has value 1, turning to value 0 will also increase d by 1. And this is the main insight about the problem, because uh, basically before, the problem was that we had different definitions. Like basically a coin inside turning to gold was, like basically turning to value 1 was increasing d by 1, but at the same time a coin outside turning to a value 1 was decreasing d by 1. But we don't want these two different things to happen, so instead we just move to a clearly equivalent formulation of the problem, which does not, like which does not change the problem at all, and is still equivalent, but it makes the problem a lot easier. So uh, this is initially 0, because you think about it as initially 0, and this is silver outside initially, because all of the coins initially have value 1. And now each of these coins is turning to gold, turning to value, like having value 1 with probability half. Like basically d is initially d is initially minus s naught, and what it should be is Go minus Gi. And uh, now basically Si plus So, and Si plus So, C, wait a second, yeah. So basically Si plus So, and d is initially minus s naught, and now let's assume that k of the coins had a favorable outcome for us. Favorable outcome meaning a coin outside that was one turn. Actually, in this formulation of the problem, everything is a favorable outcome for us, because every time a coin, basically a coin flips, basically turns from 0 to 1, it will every time a coin flips from 0 to 1, it will always be inside, because of the way we structured our visualization of the problem. And whenever a coin outside turns from 1 to 0, it will also always increase d by 1. So basically, let's say k of the coins turned, because turning is always a favorable outcome for us, and d plus k should be greater than g naught minus Go minus Gi, and d is initially minus s naught, so k should be greater than Go plus So minus Gi. And out of Si plus So, we need to choose greater than GO plus SO minus GI thing. So basically, let's say GO plus SO minus SI is equal to, let's say, X. Then this is basically K choose K because plus so on until K choose X. And obviously you need to do some case handling where X cannot be less than 0, or when X is greater than K just directly return 0. But the main part of the problem is this, and the thing is K is always fixed because it is Si plus SO, which is the total number of silver coins. So you can just do make a prefix, pre-calculate a prefix sum on this, and for each query you can just answer in O log P time or whatever. So basically, full disclosure, this is actually the editorial solution, and when I solved this problem in contest, I actually used a much messier way, which was like I didn't think about this clever formulation where uh, the points inside are. I was just thinking about like S I C X times S O C M plus X, like expressions of this form, and basically that also gives you the answer, but it's a much less elegant and a much harder way to solve the problem, and the editorial solution was really cool, so I just thought I would share it. Basically, in this way also you do get the answer, but it's a lot harder. Basically, the idea is to use Vandermonde in this case to turn it to S OCSO minus M minus X, and now you have some expression with a constant sum, and then you can just do things with it, and it's actually like very hard to simplify correctly. So basically, I did that, but the editorial solution was really cool, so I thought I would share it. So yeah, hopefully everyone got this, and the next problem is this one second. Yeah. People are okay. I'm sorry, I didn't see that you guys were waiting to be like this. Okay, so the next problem is this one. Uh, so basically, you have two binary strings A and B of length n, and the index size chosen uniformly at random, and AI will be flipped. Like it does not matter what it is, it will be flipped. And what is the expected number of moves required to make both strings equal for the first time? So basically, here what you can observe is that only the fact whether AI only whether AI is equal to AI or not matters. So basically, you can replace the two binary string formulation with one binary string, and obviously, since you flip regardless of its values, whenever you encounter an index, you flip it regardless of its value. So it's always going to be either from AI equal to BI to AI not equal to BI, or from AI not equal to BI to AI equal to BI. So basically, your entire structure can be described by only one parameter, that is k, which is the number of mismatches uh, between both the strings. And the thing is, uh, basically, let's calculate dp of k, where dp of k is the expected number of moves required uh, get to both strings equal for the first time after when you have k mismatches. So basically, you already do one move. Uh, so if k is zero, yeah, obviously a base case is that if k is zero, then dp of zero is just zero because you don't need to do any more moves. And for k greater than or equal to one, for k greater than or equal to one, the thing is either uh, you uh, have a probability of k out of n of either fixing a mismatch, because whenever you encounter a mismatch, you will basically, if it is a mismatch, you will fix it, and if it is not a mismatch, you will make it a mismatch. So basically, either you have a probability of k by n of choosing a mismatch and then fixing it, so in which case you go to dp of k minus 1, and either you have a probability of n minus k by n of uh, choosing something which is already fixed and mismatching it again. So this is the recurrence that you get. So basically, now the thing is that this is not too bad to solve actually. Like I will just tell you my code, what I did. Okay. Okay. So basically, this tells me in my code I have done the number of matches instead of the number of mismatches, but it's pretty much like the same thing. So basically, my code, what the idea my code uses is the fact that you basically dp of n plus 1 is like it does not exist, right? So basically, dp of n can be written solely in terms of dp of n minus 1, like some function of dp of n minus 1. And dp of n minus 1 is again, and the important part is that these functions are all linear functions, and this is some function of dp of n, dp of n minus 2, and so on until, and once again, okay, this page. Okay, so once again, dp of 0 is equal to 0, and dp of 1 can now only be written only in terms of dp of uh, can be written only in terms of dp of 2. And now let's say dp of 2 is like k or something like that. Okay, so dp of 2 is k, and since you know dp of 1 as a function of dp of 2, you can write dp of 1, like you know that as some function, linear function of dp of 2, you can write dp of 1 as a into k plus b. But now dp of 2 is some linear function of dp of 1 and dp of 3. So basically, dp of 2 is uh, some linear function, and dp of 2 is already, we know that is k. So basically, and we also know dp of 1, so it's 1 plus a times like whatever, like 2 by n times dp of 1 plus n minus 2 by n times dp of 3. So basically, you can find out dp of 3 in terms of k from this, and then you can find out dp of 4 in terms of k, and so on until you can also find out dp of n in terms of this. But since you already know dp of n minus 1 in terms of k, and you also know dp of n in terms of k, and like basically, and the key part to observe here is that you got dp of n in terms of k from this relation. So you basically now have one extra relation, this last relation here, that you have not used yet. So uh, this is some function of k, this is some linear function of k, this is some linear function of k. So both are linear functions of k, so you can solve from k for k from that, and then you can calculate all the values that you have found in terms of k, and in the end you can output dp of like the number of mismatches that you have. So basically, this is kind of hard to explain, so I will just share my code, and you can And the thing is, I kind of messed up here, and I told this in terms of the number of mismatches when I should actually have told it in terms of the number of matches, because that's what my code is like. So, but it does not differ that significantly. So you can just see the code if you want to. Like after the lecture, if you want, if you are not able to implement, you can just see the code. Uh, and let's move to the next problem. Now the next problem is not actually like combinatorics per se, but it's like it is counting. So I and it illustrates a kind of nice idea, but the implementation is really bad. So uh, like uh, but it's not that like basically the implementation is really bad, but the idea is quite nice, so I decided to take it. So basically, you have a permutation of all integers and a permutation of integers from 0 to k minus 1, and k is from 1 to 10 to 2 into 10 to the 5. And array of length nk is defined as follows, and pi times to the qj. So basically, like in the first thing you write p, like in the first element you write p naught times 2 to the q naught, and then you write p naught times 2 to the q1, and so on. uh, yeah, so basically you write all of that and so on, and then in the kth element you write p 1 times 2 to the q naught, and then p1 times 2 to the q1, and so on. Now uh, what you'll wait a minute. Yeah, so now what you want to do is find the number of inversions in this array. So obviously you might think about like Fenwick tree or something, but the thing is there are two problems with this. One is that pi time like qj is from 1 to 10 to the 5. Yeah, 0 to 10 to the 5. So that's already, and the array is of size nk, which is like 4 into 10 to the 10. So obviously that does not work. But let's think about what if the array was just 2 to the qj. Like basically the uh, this, yeah. Basically, let's say the pi were all one, and let's just say we had, so basically pi times 2 to the qj is eliminated, and that's just qj. So now let's think about uh, how you would find the number of inversions in such an array. Now 2 to the 8 is greater than 2 to the b. Now 2 to the a is greater than 2 to the b means that uh, a is greater than b directly. So that case is really easy because you can just count the number of inversions in the original array. Let's say like q1, q2, so on until qk. Okay, now it's 0 index, right? So q1 and q0, q1, so on till qk minus 1, and q0, q1, so on until qk minus 1. And you can just count the number of inversions in the original array, and this array is repeated n times, q0, q1, so on until qk minus 1, and only this array is repeated n times. So basically, if you wanted to calculate the number of inversions in this array, then you would first go like uh, okay, so let's just calculate the number of inversions in this array first, and then I will do the same thing for every single array here, and then multiply that by n. But that is only the pairs which appear in a single block. Like you divide this array into n blocks, and that is only the pairs of inversions which appear in the same block. But what about different blocks? So in different blocks, if one block is greater than the other, if one block is like the index of one block, let's number the blocks from 0, 1, 2, and minus 1. So basically, if the index of one block is greater than the index of the other block, then the elements of that block will always appear later than the elements of the other block, even if you take the last element of that block. For example, if I take these two elements, this still appears later than this. So if qk minus 1 is greater than q naught, it will still count as an inversion. So basically, for each block, I just need to count the number of blocks that appear. For example, let's say this is block, let's say b. So n minus b minus 1 times the number of uh, elements less than qk minus 1, and it does not matter whether they appear, their position in the array does not matter, like regardless of whether they appear later or earlier than qk, less than qk. Yeah. Regardless of whether they appear later than qi or regardless of whether they appear later than qi or uh, before qi, it does not matter because the we already counted the inversions within the block, and we are just counting the inversions outside the block now. Basically, the inversions where the two elements lie in different blocks. So basically, this is just going to be n minus b minus 1 times the number of elements less than qi, regardless of their position. So this is how to solve that problem, and hopefully you guys already know how to find the count of inversions passed using a Fenwick tree, because like this obviously requires that. Uh, so basically, that is the solution to this task we developed for ourselves, like this simpler version of the problem that we developed for ourselves. Now, let's tackle the original problem, which is like this PI times, okay, wait, my not working. So PI times 2 to the QJ, right? So basically, one observation that you can make is that what if we could do the same thing here? But sadly we cannot, because Pi is greater than 2 to the Qj, Pi1 is greater than 2 to the Qj1 is greater than uh, Pi2 times 2 to the Qj2. That does not mean that 2 to the Qj1 is greater than 2 to the Qj2. But sorry, that does not mean that Pi1 is greater than Pi2. But now you think what basically power sets of 2 are really large compared to some like random number in range 2 into 10 to the power or something. So if these powers are sufficiently far apart, then we can basically say uh, for sure that uh, this will be greater or this will be lesser than this, right? Like basically, let's say Qj1 is greater than Qj2 plus 20. Then you can always say, regardless of whether, let's say this is 1 and this is n, yeah, this is 1 and this is 2n minus 1, because that's the worst case scenario. So this is 1 and this is 2n minus 1. Even in that case, even if you make this the largest it possibly can be, even in that case, this is 1 and this is 1, 0, 4, 8, 5, 7, 6, 1. which is like 2 to the 20. So 1048,576. So even in that case, this should be greater because 2 n is like 2 into 10 to the 5 or something. So this is always greater. And uh, vice versa. On the flip side, if we assume that qj1 is less than qj2 minus 20, in that case, it does not matter what pi1 and pi2 are. It will this inequality will always be flipped. Like this will always be greater than this for similar reasons. So basically, for each j for each power of 2, there are only a certain number of uh, powers of 2 that you need to check, because the rest, like basically for each j you only need to check powers that lie in the range j minus 20 to j plus 20, because all the rest already have a deterministic outcome. Basically, everything else will either be an inversion or won't be an inversion. The value of pi does not determine it, and for these ones, you can like basically you can just apply the standard definition like pi. And yeah, obviously, this one thing I should mention: this solution already assumes that you found the inversions in the uh, original array, like inside your block, by using like whatever preferred method you have. Like this assumes that you already found the inversions inside the block, and you are only trying to find the number of inversions where the two elements are in different blocks. So, like we did here, like q1, q2, so q0, q1, so on until qk minus 1, and you repeated that n times. So basically, they are inside them being inside the same block is a kind of pesky case that you need to handle properly if uh, you are to do that. So basically, yeah, that's the main idea of this problem, and the rest you can see here. Okay, these are little, like, kind of kind of bad code, but whatever. Okay, so basically inside the block you only need the inversions of qi, because the pi values are going to be the same. So basically it reduces to what we did in this subtask, which is just n times the inversions. And now we are trying to count uh, the other, but I mean the inversions where the two elements are in different blocks. So basically, what you need is that like I am iterating the difference from minus 19 to 19, and I'm just applying the condition. And uh, by the way, it's just like normal inversion counting where you use a Fenwick tree in conjunction with your main solution. And basically, yeah, you just need to take care of the mod. Basically, the main idea is not that hard, but just working out the details is really painful. So this had like very few solves in contest because it was very hard to implement. So anyway, yeah, so I think you all got the main idea, which is that if you need to only you only need to consider small differences. You don't need to consider very large differences between powers of 2, because they will already be deterministic whether that element should be greater than the other element or should be less than the other element. And yeah, and also one thing that simplifies the implementation kind of is the fact that you are given that pi are odd. So you don't need to worry about elements being equal, because the V2, if you know what that is, like basically the power, the highest power of 2 that divides each element will be different in different blocks, and also it will be uh, the same in each block, but in each block the elements themselves are different because you are multiplying pi times 2 to the qj. So Yeah, so basically, you don't really need to worry about equal elements. That's one good thing which kind of simplifies the implementation. Anyway, I actually wrote a kind of better version of this code afterwards, so I will send those here. So hopefully you all got the key idea of this problem. Like the implementation is not that big of a deal. Like you probably can do it if you have enough time, but in the end, the main part is that you got the key idea. Okay, so we still have 18 minutes left. So uh, this, and I think all my problems are probably over. Okay. All right. This is kind of. Oh yeah. Oh yeah. Okay. Yeah. This problem. Okay. Uh, let's do this problem. One last problem. Okay. Okay. Basically, this problem is like basically you are given a tree and like you are given a binary tree and in the that binary tree you are given the values of certain vertices. They are already fixed and you need to you need to pick the values of the other vertices such that this is a binary search tree. And a binary search tree is where the values in the left subtree are less than equal to the value at vertex x. Like basically the values in the left subtree are less than or equal to the current value, and the value at the right subtree are greater than or equal to the current value. So uh, that is a binary search tree. And so basically, this problem is such that just one observation gives it, which is the fact that uh, let's consider any binary search tree. Okay, here. Uh, okay, that's it. That's one. And the slightly bigger one. Let's say this is 4. This is 3. And this is, let's say, 6. Let's say 5. 7. This is, let's say, 2. Okay, wait. 1. This is, let's say, 0. This is, let's say, 2. So now let's consider uh, the, uh, not actually the normal DFS order, but let's consider an order where we first visit the left subtree, then we visit the root, and then we visit the right subtree. Like if you have done some leak code problems or something, this will probably be a familiar ordering where basically you are visiting this subtree first, and then you are visiting this subtree, like because we don't have any right child anyway, and then you are visiting this to 0, then you are going to the root, which is 2. Okay, I think I messed up with the numbers. Maybe. Uh, okay, whatever. Less than or equal to? Yeah, less than or equal to. Okay. So, whatever. Okay. So 0 to 3, because you now visit the right vertex, and 3 and 4. And now it is not too hard to observe and also to prove that the if the tree is a binary search tree, then the this ordering of that tree, like when you perform a DFS on that tree, this ordering that you get will be sorted. And now this basically reduces to you are given an array with some blanks, and this is a necessary and sufficient condition by the way, because this encodes all the inequalities needed for it to be a binary search tree. So it's not too hard to do. You can just prove it yourself. And now this reduces to you are given an array, and certain values are filled in, but certain values are blank. So you need to find the number of ways to fill the blanks with values in the range 1 to C such that the array is sorted. And this is really easy to do. Basically, first check whether the values that are given to you are sorted or not. If they are not sorted, obviously there are zero ways to fill in because they are already not sorted. So you can't add stuff to make it sorted. And if they are indeed sorted, then just do like this, like one, 2, 3, let's say. And let's say you have 4 elements here. Let's say you have 3 elements here. So you have 3 elements here. Uh, and basically you and let's say C is 5, and let's say you have 4 elements here. So basically these 3 elements can only be 1, 1, 1. These 3 elements can only be either 1, 1, 2 or 1, 2, 2. But you let's say you're thinking about how to do it a bit smarter. So basically what you can do is that you have 3 slots, and you need to pick stuff in the range 1 to 2, which means you have 2 choices for uh, this, but duplicates are allowed, so you need to uh, add 3 minus 1. I will tell why do you do that in a bit, and basically then you choose 2 minus 1. So basically, this will be the answer, and you can check that this is indeed the answer because this is 4C1, which is 4, and this is 1, 1, 2 or 1, 1, 1 or 1, 2, 2 or 2, 2, 2, which is 4 ways. So basically, why does this give the correct answer? Because basically, if you had no duplicates, then this was really easy. You could just have done like the number of ways to choose 3 out of, okay, let's do this, not do 2 minus 1, let's just do 3. Okay, so 2 choose 3, you could just do that, but now you have duplicate elements as well. So basically you need to add, if that makes sense, you need to add uh, 2 other elements, 2 other dummy elements that you can choose whenever you want to duplicate. You can choose that dummy element in order to act as a substitute for the element that you already have. And since you can have a maximum of r minus 1 dummy elements, uh, you cover all possible ways here. Like this is slightly hand wavy, I guess. So you can do this using stars and bars as well. Oh, okay, wait. I just realized I did not do stars and bars. So let's just quickly do it anyway. So A1 so on until AR is N, and the AI are greater than or equal to first one. Okay. So basically you can view this as you have N dots and you need to arrange R sticks in between them such that uh, each stick, like no two sticks are at the same location, and like basically you just need to insert r minus 1 sticks in between them in order to divide them into r parts, where this part has a1 dots, this part has a2 dots, and so on until this part has a r dot. So basically this is n minus 1 tr minus 1, because you have n minus 1 slots for the sticks. You can't place a stick here because before this will be 0 dots, which is not possible because AI should be greater than or equal to 1. So this is just n minus 1 cr minus 1. And now an extension of this is when AI is greater than or equal to 0, you can just subtract 1 from all, you can view AI as bi plus bi minus 1, where bi is greater than or equal to 1. and then apply the same logic that we did here to the BI, and you get this formula, which is a more less hand wavy way to prove the above thing. And now basically now I hope you see that how you can prove the above thing, where let's say you need to choose elements in some range L to R, and you need to choose M elements and such that they are sorted. So basically, what you can do is that there will be some else, and then there will be some L plus 1, possibly 0, and then there will be some L plus 2, and so on until then there will be some R. So basically, A1 plus A2 plus so on until plus A. Uh, for the sake of simplicity, I will just take 1 to n because it doesn't really matter. You can just shift it to 1 to n to L to R. So basically, A1 plus A2 so on till n is equal to, let's say, m, because there are m elements that we need to choose, and this will be n plus m minus 1, c m minus 1, and yeah. So basically, now for each of the sorted each element of this subsequence that are given to you, like each element of the array that is given to you, you just take the previous element and then consider the array between them, and find the number of ways to fill in the numbers in that, and then just do this independently for all possible pairs of adjacent elements that you are already given, and then multiply them all together, and that's your answer, because no two uh, no, like this and this won't interfere with each other. As long as this is less than or equal to 2, it works out. Like basically, this is a valid binary search tree, or this array is sorted. So yeah, that's basically it. And it. Uh, am I audible now? Okay, okay. So like when I left, where was I? Like, did I do the stars and bars thing yet, or did I not do that yet? Uh, Okay, so hopefully uh, you can just see the recording, and I didn't really have anything else to do now, so I guess we'll just end now. Okay, so thank you guys for attending the lecture, and hopefully you understood most of the things I said, and